Hello again, AP Calculus students. Today we're looking at solving limits analytically, kind of algebraically, and some basic rules of those. Limit rules, we saw the limit of a sum, difference, quotient, and product last time, where the product and the quotient, the sum, are the difference of the limits. Three more that I want to take a look at here in basic limit rules, and that is again, the limit of a constant is that constant. So again, that would look something like this, that the limit as x goes to c of some number b will just be b. B is not being affected by x at all. So it would make sense that that limit would just go then to b, whether it's going to c or any other value. For that matter, it's just going to be the limit of a constant is that constant. And then the limit of x as x approaches c, the limit of x as x goes to c, is just going to be c. And then this is kind of, again, just a same thing as the power we saw before. The case where the limit of x to the nth power as x goes to c is going to be then c to the nth. And so that is a way I can evaluate some of these limit problems. We're going to look at 5 different, I think 6, maybe even different types of functions, and how to evaluate those limits then in this video. So first method here is direct substitution. And that direct substitution, you'll notice, is making use of what I'm going to call rules 2 and 3. The scenario here, x to the nth power, and then basically the product again rule. So in the scenario here, just do direct substitution. 3 squared is plus 2 times 3 plus 3 is going to be 9 plus 6 plus 3, or 18 then, as that particular limit. And then scenarios here where we factor and then simplify. This first numerator, if you do a direct substitution, you'll notice that denominator is going to 0 and that numerator is going to 0. 4 plus 4 minus 8 is going to 0. I don't want to say equals 0 over 0. We'll talk about that more later, but that's called a linking error. For right now, I can't divide by 0. We know that. So I have to come up with another way to do that. And so if I factor numerator and denominator for that matter, x plus 4, x minus 2 over x plus 2, x minus 2. And we have common factors of x minus 2. That'll just simplify to 1. So that is the equivalent of everywhere except when x is 2. That's the equivalent of x plus 4 over x plus 2. And we saw that last year in pre-calculus. That's not something new for us. And so if I now substitute, I have 6/4 or 3/2 as that limit. So we have previously conjugated denominators when I simplified fractions. It could be either the numerator or the denominator that I actually end up conjugating here. I'm going to multiply by another name for 1. X plus 1, the conjugate of that numerator. Again, I know I have to do something because I can't divide by 0 in that situation. So something has to be done different. And so when I do that, I get x plus 1 minus 1. That's just the difference of squares. So each of them squared and subtract. And then over x times the quantity, x plus 1 plus 1. And that I want to make sure that we recognize that is still a limit as x goes to 0. And so the numerator will simplify to just x. And again, the x over x will simplify to 1. And so I have 1 over, and using direct substitution, the x's again are now gone. Square root of 1 plus 1 is going to be 2 as then a final answer. So again, direct substitution from here. Again, after I realize, of course, that I've simplified the x's, putting in 0, square root of 1 is 1 plus 1, 2 in the denominator. The 1 came from the simplifying process of with the x's. All right, so a fraction action problem is a problem just involving fractions, addition, subtraction, simplifying complex fractions, as the case here. So without maybe doing the whole thing, I'll at least start that problem. I would take, this is actually a problem, I believe, right out of the notes, so you can check and see the solution again. But I'd multiply by 3 times the quantity x plus 3 over, count for all the factors, 3x, well, no, just 3 times the quantity, x plus 3 over itself, which is another name for 1. Let's do that first step anyway, so you can see how that would progress. I would end up with 3 minus the quantity x plus 3 over 3x times x plus 3. And in that scenario, again, I would look at that's going to 0 in the denominator. And in the numerator, I have, I believe, negative x. That's again going to 0 over 0. So the scenario there is, again, I'm sorry about the phone going off there in the other room, but I wasn't expecting to go off again. But anyway, you would follow through there on the rest of those steps and see that you will end up getting that simplified from there. This is actually a preview of what's going to be going on in Unit 3 when I start taking derivatives. This is actually how I use limits, actually in Section 2, Unit 2. I will use this as the definition of a limit, basically, as x approaches at the derivative of a function. And the particular function, if I wanted to, this last expression I could have written as 4x cubed minus the quantity. So 4x cubed minus 3x plus 2 and minus that whole quantity. And that's the function basically I'm taking the derivative of. So it's a matter of expanding those, maybe using Pascal's triangle. I got to make sure that my exponents are matching there. I'm going to check the notes just to see which, it was just squared here, not cubed. So let me change this to a square. And then also change that to a square. But expand the binomials, simplify some terms, and again, divide through by h. And that ends up working out fairly nicely. And then the last thing that we might see would be piecewise functions. We want the limit of f of x as x goes to 2, where x is this piecewise function. When x is greater than or equal to 2, it's 3x squared minus 2 or minus 1. And when x is less than 2, f of x is 5x plus 2. So the left-hand limit, so I want to try to find the limit again of a function. We know the limit only exists if the left-hand limit is equal to the right-hand limit. So the limit as x goes to 2 from the left. I'll use the bottom of the two functions. Here's the values as x is getting close to 2 from the left. And the limit of 5x plus 2. And compare that to the limit as x goes to 2 from the right. And for values that are bigger than 2 from the right, I'm taking the limit of 3x squared minus 1. Well, this limit would be 10. That's not negative 2, remember. It would be 10 plus 2. The left-hand limit's 12. And the right-hand limit, if you put in a 2 for there, 2 squared is 4 times 3 is 12 minus 1 is 11. But again, since those are not the same, 12 is not equal to 11, here then the limit does not exist. And again, it doesn't exist because left-hand limit's not equal to the right-hand limit. So you can check these two problems out. This is example 9, I believe, in the notes. And then this problem here ends up being the scenario here. The x's again will cancel. This ends up being example 8 from the notes. And I believe I kept all these are just right from the notes. And this again, example 10. So check those out for further work there. And you can see how those others end up simplifying if you need to. But those you probably have filled out already. So I just wanted to kind of give you a little heads up on those. Take care of yourselves, and we'll see you next time.